This is going to be an unusual lecture number 28. I'm going to present a new working paper of mine that I'm going to be presenting at UCLA on Monday. And this paper is jointly written with my good friend Niels Kok and one of my heroes in economics, John Quigley, who passed away in May and was a great friend and a hero of mine. And I'm proud that we've written this paper together. This paper is about electricity consumption of commercial buildings. We're going to present some new empirical evidence. So whenever we consume electricity, when that electricity is generated using fossil fuels such as coal or natural gas, you exacerbate the climate change externality. And the commercial sector, which is the dotted line that you see at the bottom of this graph for the United States that goes from 1960 to the present, shows that commercial buildings are a growing share of electricity consumption in the U.S., and that the residential sector has been relatively flat. Look at that convergence over time between commercial and residential. And again, this is another graph showing the rising share of commercial electricity within the real estate sector. And so these graphs together show you that over time, commercial real estate is becoming a more important part of the carbon externality. But we know very little about it because of bad data up till this point. Within buildings, whether it's some commercial building in downtown Manhattan or some strip mall, a large share of the electricity, to the right you see our sample, the Kahn, Kok, Quigley sample, versus the 2003 commercial building electricity consumption survey. And you can see that air conditioning, HVAC, lighting, and miscellaneous uses all have big shares in our sample. We're going to be looking in California where less air conditioning is used, but it's still a sizable part of the consumption. What we do in this paper is we have some terrific data and we take a new look at basically which commercial buildings at which points in time consume a lot of electricity. We're going to have construction characteristics of these buildings, such as their square footage, some data on their durables they have embodied them. We're going to know what model year they were built in, but there's also certain unobservables, such as the amenities bundled into them and their architecture, that we won't observe. There's certain interesting economics, as we discuss in point number 2 here. There's a question of how lease contracts are written. So a standard issue is, do the tenants in a building, are they paying their own electricity bills? If they have a full gross lease, then they face a zero marginal cost for electricity consumption, and by the law of demand, they're going to consume a lot of electricity. In contrast, those tenants who have a triple net lease face a positive marginal cost for electricity consumption and have the right incentives to conserve. And we're going to test for whether we see differences in electricity consumption in observationally similar buildings, depending on the contract types for the tenants. We also know the share of a building's tenants who are government tenants, and we conjecture that government tenants are going to consume more electricity because of soft budget constraint issues. They're paying taxpayer money, not their own. We have additional hypotheses we're interested in testing. The human capital hypothesis, and this is something I'm passionate about. Is it the case that if buildings have building managers on the premises, all else equal, do they consume less electricity? Is it the case that wise human management, sort of the scientific approach to business decisions, conserves on natural capital like electricity consumption? We're also going to look at individual buildings and track their consumption over time. Is it the case that as the horrible 2008 recession takes place, as unemployment rises, do we see commercial electricity consumption decline? We're also going to look at climate conditions. Is it such that on hot days, how much more does electricity consumed in such buildings increase by? And is there evidence of a rebound effect, such that buildings that are newer, which have a newer air conditioning system, actually consume more electricity during hot times because they face a lower marginal price of setting the thermostat lower because of their efficiency? So this is the classic rebound effect, that improvements in efficiency can cause increases in electricity consumption because of behavioral change. And we're going to document evidence in favor of that hypothesis. Our data. What made this paper possible is we teamed with a California electric utility who provided us data for thousands of commercial accounts, and we merged this by street address to the CoStar database. And so for the subset of commercial buildings that have been sold over the 2000 to 2010 period for a specific electric utility, we're able to create this merger of administrative data with the actual characteristics of those buildings. And then by merging other data in, we have this cool merger where we have, and we're going to use basic econometrics, we're going to have data on the building's energy consumption per month, characteristics of the structure itself, characteristics of the tenants, so sort of the property demographics, and we're going to merge in other data, knowing the street address of the building, able to merge in climate data, and knowing the month and year when the building's data was reported, can merge in the unemployment rate. Here are some descriptive statistics where we merge in, where we just show you some statistics. So for example, from this slide, you see that the typical building is consuming 1.1 megawatts of electricity per day and is spending $131 a day on electricity. And you see the building size in square feet, and you see sort of the data we have here. We estimate econometric models such as this, so the dependent variable is the log of average daily electricity consumption per square foot in a building at time t. And we're going to explain this variation across these buildings as a function of building characteristics and a bunch of other characteristics. We're going to include a variety of fixed effects to control for weather and for electric utility price data. We recognize that in running this regression using ordinary least squares, we're implicitly assuming that there isn't this sorting on unobservables by tenants. For example, if those tenants who expect to consume the most electricity and want to face a low bill migrate to those buildings that are the most energy efficient, we might actually think that energy efficient buildings are not so efficient because of this tenant mix, this selection on unobservables. So throughout the paper, we present a variety of results, and I'd like to just show you a couple of them. In this regression here, take a look at the coefficient on the renovated dummy of 0.268. What this means is, all else equal, a building that has been renovated consumes 27% more electricity than if a building with similar characteristics had not been renovated. This is going to be one of the themes that runs through these slides. When you renovate, you improve the quality of a building. The quality of a building and electricity consumption are complements, sort of like peanut butter and jelly. And so quality of building, which we expect to increase over time, is positively correlated with electricity consumption. And we see this again here. The omitted category here is Class C real estate. Class C real estate is lower quality. And take a look that relative to Class C real estate, all else equal, Class A, the best quality of real estate, consumes 20% more electricity. Again, higher quality buildings consume more electricity. And so this is a theme that repeats itself throughout these slides. We also find that contracting matters. So recall what I was saying before, that those who have a full service lease face a zero marginal cost of electricity consumption. So compare in column 1 the coefficient minus 0.168 for the coefficient on triple net lease relative to the coefficient of 0.112 for full service. Intuitively, what this means is those buildings which are triple net, where the tenants pay their own electricity, they consume 27% less electricity than those buildings where the tenants are not paying their own electricity. Also notice the positive coefficient on fraction occupied by government. In those, a 10 percentage point increase in the share of the building occupied by government is associated with a roughly 4% increase in electricity consumption. We also have data on which buildings are Energy Star. Oh, I skipped one. Notice that those buildings with on-site management of having human capital consume 7% less electricity. We also study whether those buildings that are Energy Star labeled consume less electricity. And so what you see is, in column 3, is it depends on the occupancy rate of the building. For those buildings that are fully occupied, yes, there's a large differential that Energy Star labeled buildings are much more energy efficient. I will come back in another lecture to the dynamics. I think the results I'm most excited about are the cross-sectional results that we just discussed. Those results related that higher quality buildings consume more electricity. Buildings with better managers consume less electricity. When government's a larger tenant, those buildings consume more electricity. And when tenants face the marginal costs of their actions, the law of demand holds, and those buildings with triple net leases have lower commercial electricity consumption. In the paper, because we have indicators of what type of commercial space it is, we're able to contrast all commercial real estate and break it into office, flex, industrial, and retail, and this hasn't been done before, and to study the dynamics. And we do find, and perhaps this is one of the final points I'll make, this is a graph of how our estimated effects of lease contracts differs as it gets hot. So folks, recall that a triple net lease means that you pay your own electricity bills, while full service, the dashed line, means that you don't. What you learn from this is when it gets really hot at our electric utility, and if you're a building where you don't pay for your own electricity, you are a full service, you increase your electricity consumption by more than those tenants who do face their own marginal cost. And we also find that newer buildings are more responsive to heat shock. So this is our evidence of the rebound effect. So again, what we're graphing here is we're comparing all buildings at our electric utility to new buildings, those built in the last 5 years, to those buildings built more than 50 years ago. And we're reporting evidence here that when it is hot and you are a new building, we're seeing those buildings actually consuming more electricity. And given that these new buildings have new durables in them, this must be the rebound effect at work. The more efficient durables, you can set your thermostat lower and achieve more comfort on a hot day because you face a lower price per degree of comfort. And so I will stop here, but this is an example of new research, new empirical research on commercial electricity consumption, and it will soon be released as an MBR working paper.